Record. Okay, let's get started. So today we're going to do continue with lecture 5 for MRI. So before we get started, are there any questions about course logistics or what we talked about last time? Okay, so everyone knows project proposals due next Monday. Um, if you want feedback beforehand, just make sure you can email me or come talk to me after class. And happy to provide feedback before you submit your proposal. Okay, so today we're going to cover sort of finish up our discussion of sort of traditional MRI, and then we're going to switch gears a little bit. Yeah, question.
The proposal we just send right to your email, right? Or is that
I think it says Gradescope, right?
is it a grade scope time?
Yeah, so basically you'll submit to Gradescope. I'll look at it. If it's okay, I'll just say, yeah, good. Otherwise, I'll just say follow up with an email to me just so that, the back and forth, I'm not having to check Gradescope so much. Yeah, good question. Being transcribed. Okay. Um, and then we're going to sort of switch gears and talk a little bit about how imaging is actually done today, which is more sort of from a linear algebraic point of view. So hopefully today will be the really last day of lots of math, and then the following lectures will start switching into more applications of MRI, and sort of you'll see how MRI is used. All right. So if you can make it through this lecture, you'll be through most of the hard part of MRI, and so just stick with me. So the main concept we talked about last time was discussing case-based sampling. And the question is, given an image that has a certain field of view, so it's a certain width and height, and also it has a certain resolution requirement, how do you decide how to sample case-space? What's your delta kx and how far out do you go in case-space? So the nice thing is it sums up to four really sort of easy to understand and remember equations. Basically, whatever parameter you're given, whether it's FOV or resolution, you just take the inverse of it. Okay. So I think everyone did pretty well on the pre-lecture quiz, but just remember where these equations came from is, for example, for delta kx, I want 1 over delta kx to be greater than the field of view, right? So basically, um, uh, I sort of need that to sort of this should be true. So if I don't set it, so this is the Nyquist criterion. And essentially for our design equations, we just set this to equality. Okay. But as we saw last time, sometimes there will be cases where you set that delta x equal to 1 over field of view, and your system will actually come up with a message and say, well, I can't really do this. Okay. And sometimes they'll just propose a new set of settings for you. It'll say, we recommend you do these settings. Other times they'll just, in the older days, nowadays with AI and everything, it'll propose something new. In the older days, it might just say, make it bigger or make it smaller. Okay. So if you end up with something where it can't do that, then you know that you have to somehow sort of change your parameters such that in this case, for example, this delta kx is less than the field of view means that delta kx should be less than 1 over the field of view. Right? Okay. So because, or is it be greater than, right? It's greater than, right? Or is it less than? No, it's less than. Okay. It's less than 1 over the field of view. Okay. So if my delta K is too big, it means my field of view is too small. So in that case, I'd have to increase the field of view so my delta K is less. All right. Okay. Let's rewrite this as clear. Delta Kx is less than 1 over the field of view. Okay. So in terms of your homework assignments and what you sort of need to remember is this is pretty easy to remember. Delta Kx equals 1 over the field of view. And then we looked at the special case of a spin warp where we were sampling with a gradient sort of like this for the readout direction. And we said that delta Kx in this case is gamma over 2 pi times gxr times delta t. The key thing to remember is this is the area. Okay, so it's the area that takes us one delta K. All right. And so for your homework assignments, you know, the formula for the area might be slightly different. Okay. Or whatever it is, you need to figure out what that area is. And it's essentially whatever area moves you one increment of delta K is the area you're looking for. Similarly, for the WKX, okay, you're looking for the area here that takes you from one side of K space to the other side of K space. Okay, so in this case, it's this full area. Okay, so it's always about what's the area that gets you the distance you want to move. All right, so that's for the redout gradient and spin warp. In your homework assignments, I think, you've got probably something like this, a square gradient, or you're going to have something like this. Okay, so essentially, these are the kx, the K space trajectories, right? Remember, the K-space trajectory represents sort of the integral of the gradients. And so essentially, if you think about what areas do you need to make those movements, that's what you want to think about. So think about the areas. All right. So that sort of can help you sort of focus on what you need to figure out. So for the phasing cogradient, remember the way we get each of these lines is we change this amplitude here. Okay. So now the incremental area we care about is what's the difference in area between, say, this one and this one. So that increment in area would be given by something like this. Okay. So this is that area there. All right. Yeah.
Do we jump back to the origin after every pulse?
Yeah, that's a good question. So in this case here with the RF, we're assuming that we apply an RF pulse, we acquire the data, and then everything dies away, and we sort of start afresh. And so after the RF pulse, we're going to assume we start off at the center of K space. So that's the assumption you can make for this class. With more sophisticated MR, it may not be the case, but for this class, you can make that assumption. And similarly, if we're thinking about what takes us from one side of K space to the other side of K space, it's basically all this area, right? Because it's that area. One of them took you all the way down here, the other took you all the way up there. So it's that area. And so that's the area that you care about. Okay. So the key here is just to emphasize that we're just looking at areas, right? So it's always that Kx, okay, is equal to gamma over 2 pi, the integral d tau, right? It's that area where you are in time. And ky of t equals gamma over 2 pi gy of tau d tau, right? So as long as you sort of have that in mind, then really MR design is really about playing around with these areas. Okay, so let's do a quick exercise together just to try to consolidate our understanding of this. So here for a spin warp pulse sequence, now you're asked to look at the phasing cogradients to achieve a field of view of 20 centimeters and a resolution of 2 millimeters. What's the maximum gradient? And the maximum gradient strength you have is 6 Gauss per centimeters. Okay. What is the minimum width you can use for that phasing cogradient? So remember, the phasing cogradient is the one where we're going to sort of change its amplitude, but we're going to keep its width fixed at tau sub y. So basically asking for what tau sub y is. All right. So go ahead and think about that for a minute or two, and I'll open up the poll so people online can respond. Let's see. Okay, so let's take a look at this. So you're given field of view and resolution. So which parameter matters here if we're trying to find the minimum width? Sorry, go ahead.
Uh, the field of-
The field of view. Okay, so the field of view is determined by sort of this area here, right? Like that incremental area, right? Okay, so will that determine your minimum width? Maybe not. Okay, so the field of view, you could start there, but you'll quickly find out that actually what you need to do is look at the resolution. Okay, because that determines what's the maximum area. And if you're thinking about, I'm limited to the gradient of 6 Gauss per centimeter, then that determines my maximum height. And so then therefore, you know, that determines my width because my area is going to be limited by that. So if you think about it this way, what we really care about is um, basically I can go 6 centimeters this way, 6 Gauss per centimeters this way. Okay. And so I want this whole area, right? That's the area from one side of K space, the other side of K space, right? And that's tau sub y, right? So I need to know, so this height is 12 Gauss per centimeter, right? So I know that I ideally want gamma over 2 pi times 12 times whatever my tau sub y is to be equal to what? 1 over the resolution, which is 0.2 centimeters. Okay, so that's 5 inverse centimeters. Okay, so that means I want tau sub y equal to 5 over 12 over 4,000. Okay. And so what is that? That's 5 over 48,000. Okay. Equals 5 over 5 times 10 to the, roughly 5 times 10 to the 4, right? Something like that. Okay. So that's about 1 times 10 to the minus 4. So it looks like 100 microseconds would be your closest one. All right. So there again, you're given a design constraint, and you know you're trying to get a certain maximum area, and so that determines what's the minimum width you can have, temporal width. All right. So I think those are sort of the types of, this is sort of the level of complexity of what you'll need to do for the homeworks. It's nothing more than what's the area. All right. So yeah.
Sorry, confusing my FOB. So,
Mm-hmm.
this last time we were doing it, the FOB was important. That determines the size. Could you just re-explain?
Sure. So in this case, we want to, this area is the area that's going to get you from the bottom of K space to the top of K space, right? And so that's related to WKY, right? And so we said WKY is equal to 1 over delta Y. And delta Y in this case equals 2 millimeters. Okay. So this is basically WKY, right? So gamma over 2 pi times that entire area is going from the bottom of the K space to the top of the K space. Does it help?
Okay.
What? Yeah.
I definitely do more practice, but yeah.
Okay. Yeah. Okay. Hopefully by the time you're done with the homework, it'll be more obvious. All right. Okay. So let's talk about a couple of things that are sort of interesting things that now that you have some basic understanding of how MR works, if you ever see these in the clinic or in your research, or even on an MRI scan that you get of your knee or something, then it'll make a little more sense. So what I'm showing you here on the left side is a 256 by 256 image. So there's 256 voxels this way, 256 that way. And it looks pretty good, right? Okay. So if you acquire that image, you're like, oh, that's great. Okay. So on the right side, this image here is now we've acquired 256 this way, but only 128 this way. Okay. And what do you guys notice different about this image? Is there anything wrong with this image now? Yeah, you're seeing what's called a ringing artifact. You guys see these edges here? There's that rippling, okay? So on a phantom, that's sort of, oh, that's sort of cool. But if you were looking at, say, like they had an MRI of tendons in your knee or something, or anywhere there's a sharp edge, if they see these ripples, most radiologists can probably read through them. But ideally, you'd like to try to get rid of these ripples, right? So they don't interfere with the diagnosis. So one of the things we want to figure out is, well, what causes these ripples and how do you maybe minimize them and how do people actually minimize them in practice in the clinical domain? So the idea is we have an edge, right, in our image, right? So like that phantom just ends and that's the edge. And remember, when we multiply in K-space, we're multiplying by something that has some width WKX, right? So we're multiplying by that. That means we're convolving with a sinc function, okay? And remember, the bigger we make that sinc, the bigger we make that rect, the narrower the sinc function gets. Conversely, the narrower we make that rect function, the bigger the sinc function gets. So in this case, this would be for like so this is say some WKX, right? And this would be half of WKX. Okay, and then that's going to give you a fatter sinc function. All right, because remember the less I go into K-space, the fatter my sinc function is going to be, right? Because this zero here is at 1 over WKX. Okay. So if you think about it this way, what happens is when I convolve that edge with a sinc function, I get these ripples. So this is known as Gibbs ringing. And the size of the ripples is the same regardless of which one I use, but it's just that you notice that the ripples die off faster in the red curve when I have the faster sinc function than the blue one, right? So there's still ripples there. It's just that how far they go out is much worse the fatter my sinc is. And so it's much more obvious. So one thing you could do is you could say, well, you always need to acquire this image, but maybe you don't have the time to do that, or there's some other reason why you can't do that. So the other option you could do is, and here's once again, you're seeing a Hanning window. So you saw it in CT. Here, instead of multiplying K-space by a rect function, which is like a hard cutoff of my K-space, I'm going to multiply K-space by a smooth function. Okay. And so the idea is that smooth function has an inverse Fourier transform that's smooth now. Okay. So now when I convolve it with the edge, I go from having the ripples, so that's the Gibbs ringing, to something that's smooth. Okay, so now I have a smooth transition. Okay, but what's the trade-off? Can anyone see what the trade-off might be here? Like, what have I given up by getting rid of those ripples? Yeah, it's slower, right? So you sort of see that I'm blurring out my edge a little bit. So there's no free lunch. I've gotten rid of some of that high frequency information. So now that sharp edge is going to be a little more blurry. All right. So whether that trade-off's okay or not really depends on the application. Here's another interesting thing about MR, which is sort of how we acquire images. And so just to sort of orient you a little bit to what we mean is like these are what are called axial directions. So anytime you do a transverse through the body, like if I slice the body this way, these are called axial slices. Okay. So a lot of MR images will be axial, all right, especially through the head or through the abdomen. But I can also do sagittal. So I can cut myself this way. And if I look at myself from this side, that's a sagittal. So these would be sagittal. Or it could also cut this way, right? And these are coronal images. Okay. So the idea is that it turns out that a lot of times when we want to do images, we will end up doing sagittal or coronal images for certain applications. And let's sort of see why we might do that. So imagine I wanted to just image this person's like their spine around their neck or something. And maybe I want an image of their head and their spine or something like that. So really, my desired FOV is pretty small, right? I only really care about like maybe they've like taken a fall and I want to look at their neck and see if they've got injury in these vertebrae here, right? But this is the FOV I care about, right? But the actual object FOV is like from their foot to their head, right? So I've got a really big FOV, right, in this direction. So the problem is, remember, delta K equals 1 over field of view, okay? And so it's okay having a small delta K, but now the problem is to get out to some place, to some resolution, I'm going to have to acquire a lot of lines because the smaller my delta K is, the more delta Ks I'm going to get out to some resolution. Okay, so it's going to take me forever to make that image. So I don't really want to make that trade-off. So it turns out that there's a trick. If I want to image this and I apply a gradient along, say, and we'll, in this case, it's called the x direction. I'm applying this as my gradient here. Okay. So I'm making these spins here. Any spins here will spin faster than spins here. Okay. So these will be fast and slow, just like any other gradient. And then in addition, any spins down here outside of the area I care about will be even slower. Okay, and they're actually processed at a frequency that's an even lower frequency. And therefore, since I know the MR signal is coming in as a frequency signal, I have an opportunity to say, well, let me just not look at those frequencies. They're outside my range, so I'm just going to filter them out. And that's in fact the job that this low pass filter does. Okay. So the idea is, let's say this is your field of view, but you really only care about some small part of the field of view. You can actually apply a filter that just says, just look at that part. And that's a nice way of sort of saving time. So now in MR, you have the opportunity to limit your field of view. All right. And so we'll see that again when we're looking at selecting slices. So the idea that we can make spins have different frequencies turns out to be super useful, because then we can use electronics to sort of filter out frequencies we don't care about. Okay, so that's really sort of the end of our sort of coverage of traditional MRI recon. So before I go on, are there any questions before we move on to sort of how it's done today? Okay, if there's no questions, let's do a little bit of history. So 1983, sort of what we've talked to you about today was sort of invented and sort of perfected in the 80s. Okay. And so probably no one here in the 90s would have been getting an MR scan, but maybe your parents or one of your relatives. If someone you knew was getting an MRI scan in the 90s, they would be getting everything we've talked about would apply. Okay. Basically, how they got the image was acquired and how it was reconstructed, all the theory you've learned up to now, that's how it would have been done. And then what happened is in the 90s, I think Dan Sodexon was a graduate student, postdoc. Okay. A few really smart grad students and postdocs came up with a new way of doing MR, which we're going to talk about. And this is all under what we're going to call parallel imaging. Okay. And this was the first sort of major revolution in going away from standard Fourier reconstruction. And this is now, if you get an MRI done, you're going to have parallel imaging. It's now standard on all systems. So this was a really big deal. Okay. Sometimes when some things get invented, like I've seen things that are invented, there were other things that were invented in the 1990s that are still not in the clinic. All right. Sometimes it takes 30 years for something to go from like the lab to the clinic, and sometimes it never makes it into clinic. Um, Parallel imaging was such a big deal that by early 2000, scanners already had this on it. Okay. And have them to this day. The next big innovation came from another graduate student, Mickey Lustig, who came up with compressed sensing, which was another way of going beyond Fourier and going faster. Then another graduate student, Colin Setsenpop, came up with yet another way of going faster. And then the next big revolution, I would say, was some other grad students and junior faculty, which was bringing MRI into the deep learning revolution. Okay, so now, incredibly, all these things are now in the clinic. So even though deep learning is only about 5 or 6 years old in terms of MRI, it's already in the clinic. Okay. So these technologies were so revolutionary that people just had to put them into the clinic very quickly. So we'll do a fairly, at least give you an idea of the math behind parallel imaging, and then we'll sort of give you a sense of how compressed sensing and deep learning work. We're not going to have time to go into them too deeply. All right. But at least you'll have a sense of, if you go and get an MRI done, in the future, it's going to be some combination of these technologies or whatever follows them. Okay, so let's start off with just some preliminaries. And I'm going to show a lot of math, but I'm not going to really focus. I'm just going to sort of guide you through it. And the idea is there's a MATLAB grader project that sort of I'm going to go through that code here. And so in that grader problem, you're really not expected to do too much coding. You just sort of change a few parameters and just comment on what's done. So I'm just trying to guide you through that so you have a sense of what to do. So after today's lecture, you should be able to do all the homeworks. Okay. All right. So far we've been talking about like kx and ky, and now we're going to introduce what are called discrete approximations to sort of get you into linear algebra. Okay, so I know you had a problem on linear algebra for the homework, I guess, 4, and so that was just meant to sort of help for those of you who haven't done linear algebra for a while, just remember what linear algebra might be, just so that during this lecture you're not totally lost. Okay, but we're not expecting you to be linear algebra experts. I just want to give you a sense of how things are done. And in fact, if you think about all of imaging and deep learning, I mean, it's so much based on linear algebra these days that it doesn't hurt to review some linear algebra. Okay, so if I have kx and ky and they're continuous variables, discrete approximation is I just have them integer multiples of delta kx and delta ky. Similarly, if I have x and y as continuous variables, it makes sense to make them integer multiples of the resolution, delta x and delta y. And once I have that, then I can also say that if I have some field of view and some resolution, then I should have, n sub x voxels in the x dimension and m sub y in the y dimension. So just saying that I can take all this continuous stuff and get it into integers. And if I do that, what it means is I can take something like this, where kx and x are continuous, and at the end of the day, I get something like that. Complex exponential with minus j 2 pi mn over nx. Okay. And this is really nice because this is essentially what, if you look under the hood at what MATLAB does, this is what MATLAB does. Okay, when you ask MATLAB to do a 2D FFT, it just has complex exponentials of this form. All right. So the next thing we want to talk about, so basically it's saying that I've just gone from, I can go from an integral to some sort of approximation like this, where that's the part we just looked at. And in 2D, it's just the sort of the counterpart. And essentially, this is what MATLAB does. Okay, when you ask it to do an FFT, it just computes that. All right. So it's just doing this sort of discrete approximation. So the next thing we want to do is give you just a little bit of intuition behind what this looks like. So here I've got the sort of complex exponentials, and I'm writing them out for different values of the here. Let's see what we have. Okay, so here, let's say M and P are what are these? They are the frequencies. Okay, so at 0 frequency, if I let M and P be the frequencies, I would end up with 1, 1, 1, 1, and then I end up with sort of this is my very basic 2x2 image. Okay, so I'm trying to create like very basic Fourier basis functions from this, and so this is obviously at the center of K space, right? It's just all ones. Okay. If I look at some other frequency, 1, 0, 1, 1, this just means I've got some variation here. So this is sort of along my x direction, right? Oops. And here I've put in a vertical frequency, and so there is some variation along that direction. And if I have both frequencies there, then you sort of see there's the basic variation like that. Okay. So the point of this is just showing you that when we're dealing with matrices, we can think of matrices, as having spatial frequencies in them as well. All right. So what I can do then is what a discrete Fourier transform does is it just takes my image. So I could have, let's say, a 2x2 image. All right. And I can just multiply it by my complex exponential. Okay. And in this case, the complex exponentials just come out to be these simple 1, 1, 1 minus 1 things. So this, for example, would be the center of K space because I'm multiplying my image by something that has no variation. Oops. Let's see, I just erase that. Whoops. It's not good. Let's try this. Okay, I have to erase it like that. Okay, and then, sorry about that. So here we basically multiplying it by our object by something that has variation going up and down. Here we're multiplying our object by something that has variation going left to right. And here we're multiplying it by something that has variation uh, going diagonally, right? So this is just showing you the most basic Fourier transform you could do. You're taking a 2x2 object and multiplying it by 2x2 matrices that have variations in them. And then here's the most important part is I can do all that. I can take this and I can vectorize it. Instead of writing my image as a 2x2 matrix, I just take it column-wise. So I take the first column and then I put the second column underneath it. And if I had more columns, I would just stack the columns. Okay. So this is really done a lot in MATLAB, right? So MATLAB makes this super easy because this is a super important operation. So basically this is just in MATLAB is y colon, right? So this is y, it's a 2x2 matrix. And if I write y colon, it just makes it a column vector. Okay. And similarly, I can make column vectors of this guy here. So that's the column vector of that. And then I can take each of these and make them a column vector. And so I end up with, or I actually take one of these, this now becomes, and then put them as the rows of here. And so I can write all these operations as a matrix multiply, okay? For each one of these rows is basically one of these 2x2 matrices laid out as a row, okay? Because I want that row multiplied by the vector, right? So that's the most important thing, is that everything we've done can now be recast in the language of linear algebra, which means now we're making ourselves, we can take all the machinery of linear algebra and try to gain some intuition behind what's going on, right? So what you're going to see is we're going to look at things using sort of concepts you learned in high school. We're going to look at square matrices. We're going to look at overdetermined equations and underdetermined equations. And so everything you learned in, I don't know, 8th, 9th, or 10th grade, we're now going to see how you apply it to understand how modern MRI works, right? Okay, so just to remind you, up to now, we've been looking at things like, oh, I have my object and I take its Fourier transform and I get its K-space. And everything has been, we're looking at things the way humans look at them as object, like, a two-dimensional image, right? But to do things in linear algebra form, we need to take each of these 2x2 images and make it one long 1D image. So that's what I've done here. I vectorized my image. So here, this is now my image in vector space. Okay. So you can sort of see basically, it looks a little different, but you can sort of imagine why this is just taking this thing and looking at column by column by column by column. Okay. This is my encoding matrix, so that has all my complex exponentials in it. And then all I'm saying is if I take my object and multiply by this encoding matrix, which has all those Fourier components in it, then I get my Fourier transform. All right. So this is really nice. It basically says no matter what I do, and can apply to CT or any imaging modality, is you have your data and you multiply it by some matrix. And then your output is the measurement. It's whatever the machine is measuring. Okay, you're representing as a matrix multiplying. Okay, this is just sort of showing you once again, essentially my object here, my K-space, and I'm just vectorizing these. and everything that I'm doing in the Fourier transform, everything the MRI system is doing, I'm saying I can represent that as an encoding matrix, right? Okay, so this is just some code just to walk you through how that might actually look. So essentially, you can sort of see here, um, I'm taking my object and vectorizing it. Okay. And here you can look at this in your ledger if you're interested, but here that encoding matrix is just, I'm building up that encoding matrix. And so here I'm just taking my encoding matrix and I am multiplying it by my vectorized object. And this gives me my vectorized 2D transform. And if I want to, I could always convert it back to my traditional form by reshaping the matrix. Okay. So that's just showing you how we do it in MATLAB. And you sort of see here, you're seeing that two-dimensional sort of the form. You've got the e to the minus j 2 pi, kx of n times x, ky times y. Okay. So just showing you how things look under the hood. Okay, so now let's sort of relate this back to sort of things you learned when you first learned about matrices and systems of equations. So if I have a square matrix, then the number of equations equals the number of unknowns, right? Because this is a square matrix, right? And so we know that if E is invertible, then I can just write M equals E inverse S, right? And it turns out that taking the inverse of the matrix is essentially just doing the inverse Fourier transform. So now sort of that's a nice interpretation. And furthermore, if E is orthonormal, okay, does anyone know what we actually asked you that in the homework. So what does orthonormal mean? Anyone remember what orthonormal means? Or even orthogonal? If I have two vectors and they're orthogonal, what can I say about those two vectors? Go ahead. They're perpendicular, right? And so what mathematical operation is equal to zero? The dot product, right? Okay. So if I take the dot product of these two vectors, it's zero. And then furthermore, so that's the ortho part. Normal just means their length is one. Okay. So they're just nice vectors. So that's a nice property. So if that's the case, then I can just take the complex transpose, which is I take the transpose of the matrix and also conjugate everything, and that's going to be my inverse, right? Now we're also going to find out that the first step we're going to take is, well, what happens if I actually have more equations than unknowns? Okay, so what do you know about that from like when you first, if you have more equations than unknowns, is there going to be a solution necessarily? You guys remember from like when you first did this, when you were like 12 or 13 or 14 years old? Like, what were you told about overdetermined systems? Will there be a solution? Is there a solution guaranteed to exist? An exact solution? Don't remember. Okay. So if you ask ChatGPT, it would say no, right? So there's not a solution is not guaranteed to exist, right? But we can come up with what's called the least squares estimate. Like, what's the best solution? What's the solution that will minimize the error? Okay, and we'll talk about that. What about this? Underdetermined equation. There's more unknowns than equations. In this case, does a unique solution exist? Does a solution exist at all? What do you guys remember about this? Anything? So we'll have to leave that, and you can sort of think about that, and so we'll come to that later. So let's look at this case here. So if let's see, oh, more inner product zero. Okay, great. Yeah, thanks online. So if anyone online wants to talk about the undetermined stuff, just type that into chat. Um, so we already looked at this case. So in the case where there's a number of equations equals number of unknowns, then you can just simply take the inverse. And so one way of taking the inverse is you can in MATLAB, you can always say, take the pseudo inverse of my matrix. Pseudo inverse is nice because if it's a square matrix and the inverse exists, it'll just take the inverse. If it's a rectangular matrix, it'll do one of the operations we'll talk about later. So you're sort of safe with doing the pseudo inverse. In this case, we could also take the Hermitian transpose. And because of how we define our encoding matrix, we do need to sort of normalize it a little bit. But the understanding is the same, that basically to first order to scaling factors, the inverse is equal to the Hermitian transpose. Okay. So let's look at an example of this. So in this case, we've got this is my object. These are the Fourier transform coefficients. Okay. And the solution is simply I just take the inverse of that. Okay. I just take the inverse of that matrix. All right. And in this case, if you type this into MATLAB and you typed inverse, it would just give you this matrix. Okay. And then you just solve like you would. All right. And then you can write the equation as a sum of these vectors. And then if you wanted to, you could always rewrite it as sort of, you could go from vectors back to 2D images. Okay. And you're back to the sort of the Fourier interpretation. So we're just really going into this matrix space to sort of help with the intuition. Okay, so the first step sort of in the story, the next step in the story was in the 90s, people started experimenting with like what happens if you didn't have just one coil? What happens if you had more than, what it started off with phased arrays. People started putting coils next to each other, right? Let's, for example, you want to image the spine, what happens if you had a bunch of coils to image the spine? How would you actually combine those images to make one nice image of the spine? So that's the first question we're going to answer, okay? And then very quickly, within about 5 years of that original paper, people started realizing, oh, I can actually use the fact that I have multiple coils to go faster and acquire my image much more quickly, okay? But let's do the first one, which is an example of overdetermined system. So in this case, in this image, we're looking at a head, and we've got 8 coils around the head, okay? And if you look at any one of those coils, if you look at the image, you notice that they all look the same. They all have similarities in that they're all an image of the same brain, but their shading pattern is very different, right? This is indicating where the coil is, okay? And you notice that the image is always brighter next to where the coil is, right? And that sort of makes sense. So if I have a coil here, it's going to be most sensitive to the spins that are closest to it, right? And then if I have a coil here, it's more sensitive to these spins, right? So it's going to get more signal from the spins closest to it than the ones farther away from it, right? So what that means is that I'm going to have my image multiplied by what we call a coil sensitivity pattern. All right. And so we're going to represent that as some matrix C. Okay. And so this means I have my object here. And before I encode my object, I multiply it by, say, coil 1 is going to multiply by its sensitivity pattern, coil 2 by its sensitivity pattern, and coil 3 by its sensitivity pattern. Okay. Then I multiply by sort of the Fourier encoding pattern, and then I store all that data. So now for every coil, I have a full Fourier space, right? I've got the Fourier transform of this guy, the Fourier transform of this guy, the Fourier transform of this guy. So I multiplied each of those sort of images by the Fourier transform encoding matrix, and I'm going to get this data from this coil, this data from the second coil, and this data from the third coil. So now that I have way more data than I need, right? Basically, I only really needed one coil, but if I just had one coil, I would end up with not my object, but I would end up with the object multiplied by the coil sensitivity pattern, which is not what I want, right? I don't want a shaded image necessarily. What I want is something that actually looks like my object. So the question is, how do I go from this collection of shaded images to an image that looks more like what my object should look like? So that's the question that we're going to answer. And that was the first thing that people figured out. Okay. So it turns out this is just S equals E times M. It's an overdetermined equation. And it turns out when you have that, then the solution always, this is basically, you can do what's called the least square solution, which is what you looked at in your homework. Okay. So this is an example of what the code will look like in the MATLAB, where, as example, we have some very simple 1D profiles, okay? So for example, here C1 is this profile here, and C2 is just flipping that profile, okay? So in the code, you're just gonna be asked to sort of play around with making up some of your own profiles and see what happens, right? This is just showing that, for example, this profile here, C1, is sort of has more sensitivity between like -15 and 0, and then it falls off. And then C2 is opposite. It has no sensitivity, and then it increases, right? And so sort of see here is where we are going to multiply my encoding matrix by those sensitivity patterns, okay? And this is where I'm making up this is the overall matrix, okay? And then here I take that matrix and I multiply by my object. And here I simply take the pseudo inverse and multiply it by my measurement data. And this becomes my estimate of my object. Yeah. For the homework, you're free to come up with any pattern you want. It's just math. In practice, you actually build the coil. And as you're building the coil, first of all, you can use EM software to simulate what its sensitivity would be. But then in practice, you actually put it onto a phantom or the object, and you can actually measure it. Yeah. So in general, you'll measure it. Yeah. Okay. So just to give you a sense of where that solution comes from is that our encoding matrix spans some vector space, right? Our data doesn't necessarily lie in that vector space because it's an overdetermined set of equations. And therefore, we're looking for the solution, some combination of my columns in my encoding matrix, this combination that makes this error the smallest, okay? And the error that makes it the smallest is the one that's going to be perpendicular to my model space, right? So this is the principle of orthogonality, which comes up like everywhere in engineering and science. And you can sort of convince yourself, if I took any other vector that wasn't perpendicular, it's going to be longer, right? So this is the smallest vector. So that's when you're doing this solution here, that's what you're looking at when you have an overdetermined system. So let's look at what that fully sampled acquisition looks like. So just going to go through the math and just going to give you the answer here, which is if I will work through the math and actually solve this and plug everything in, then I end up with this really nice solution, which is it's approximately equal to the square root of the sum of squares. So it means take each of these images, take its magnitude and square it, add them all up, and then take the square root. And if you do that, you end up with a pretty good image. Okay, so that's a pretty good approximation to the exact linear algebraic solution. So that's shown here. Here I've got coil 1 is mostly shaded bright on the left side. Coil 2 is mostly shaded up bright on the right side. And I take each of those images and square them, add them together, take the square root of the sum, and I end up with this image that looks pretty good. Okay. So here's an example in the that's in the code that's in your homework, where these are the profiles. And sort of these profiles look pretty, each coil is pretty much seeing the same thing, right? One is like just falling off this way, the other's falling off this way. These are the coil profiles sort of seen end on. Okay. And so these are the objects. This is the coil, the object times object 1 times coil 1. And this is the object times coil 2. And this is the reconstruction with, this is the exact this is the least square solution. And this is the sum of squares approximation. And you can see they do pretty well. Okay. So in this case, I've even added some noise to them, right? So there's some noise in the background, which will be important. And they're just showing you that for this coil, when the coils have these patterns that are fairly overlapping, the sum of squares works pretty darn well. Okay. Now I'm going to look at these coils, another set of coil profiles, where now each coil really has its own sort of region, right? It's a much sharper drop off. So you sort of see along this way, it's sensitive in the yellow part and it really drops off in the blue part. The other coil is at the top, it's not very sensitive, and then it really increases sensitivity. Okay. Okay, well, there was a question. What is F over again? Okay. Which slide was that on? Yes, no. Oh, F over is just this thing here. Uh, this is just the Fourier transform of my object. Okay. So basically, I'm taking my object and it's this basically, it's this S here. So this is basically what the F over is. All right. Okay, so now if you look at this case where the coil profiles sort of don't overlap, the exact with the pseudo inverse, the least square solution does pretty well, right? Okay. But now look at the sum of squares recon. It's really sort of falling apart here, right? It's not really giving you the right image. Okay. And because it turns out that sum of squares recon sort of depends on sort of having coil profiles that are sort of don't have such sharp profiles. Okay. Yeah. Yeah. So basically the the pseudo inverse would be this one, right? This is the least square solution, and the sum of squares is just this approximation.
Here,
Yeah, and so here there's an approximation here.
I can't see where.
Yeah, so this is the pseudo inverse.
Oh, no, I said on the.
Oh, it's not showing anymore. Weird. Huh. Oh, so when did that? Is it not sharing the screen anymore, or what's going on? Okay, let's stop sharing. And let's try sharing again. Okay, that's good, right? Okay. So did that just stop working or? All right. Okay, so basically this top solution here is the pseudo inverse solution. Right, that's the least square solution. So least squares. And this is this sum of squares approximation. All right. So you're sort of seeing when the coil profiles are sort of overlapping quite a bit, the least squares and the sum of squares do pretty well. And then here, they don't do so well when the coils are uh, sort of had distinct areas, right? So now let's look at the other case where we have an underdetermined system of equations. So how might we get that? Well, here we start off with a fully sampled acquisition where E is a square matrix. And then undersampling means, for example, in this case, I'm just getting rid of every other line of K-space. So I'm just, skipping every other line. Like you did in the homework. Okay, I skip every other line. And so now I'm going to have half the number of samples in Fourier space, right? Because I've gotten rid of half of them. So now I've gone from a square matrix to now one that is sort of a wide matrix. Okay. And now I have less equations than unknowns. And so the question is that I have multiple solutions that are possible. Okay. So if you guys remember from your sort of high school days, when you have an undersampled or underdetermined set of equations, you're going to have lots and lots of possible solutions. Okay. So now the question comes, it's not that you don't have any solution. Now you have too many solutions. And so now the question is, which solution do you pick? And so the one that is picked normally is what's called the minimum norm estimate. Okay. And that's equivalent to just taking this, putting in zeros where you don't have data, and taking the inverse transform. So it turns out what you did in your homework when you got these alias images is exactly this minimum norm estimate. Okay. Of all the possible solutions, it's the one that has the smallest size. Okay. What that means is, in this case, all these arrows here, this arrow, this arrow, this arrow, this arrow, this arrow, they're all possible solutions to my equation. But obviously this one has the smallest length, right? And that's the minimum norm solution that you're going to be picked. So just know that if you take a Fourier image, Fourier space, and you just start getting rid of data and put zeros in where you got rid of data and take that inverse transform, you're essentially getting the minimum norm solution. And so we know that that leads to the aliasing, right? So I can do this, but if I do this, I'm going to have aliasing, right? And that's generally not desirable. Okay. So the question is, why do we undersample? Like we know if we undersample, we're going to get aliasing. So why would we do it? Well, basically, if I don't have to collect so much case space, I can go much faster. Okay. So I can save time. And in general, if I can save time, I can also save money. Okay. And so that's one idea that, people are always looking for like the 10 or 15-minute MRI exam. Like currently, if you go and get an MRI exam done here at UCSD, it's probably going to be 45 minutes or an hour on average. Okay. The more patients they can run through, the more they can bill. And so ideally, there are some places that are trying to aim for like a 15-minute exam, okay, or even a 10-minute exam. Like you're literally the limiting factor is no longer the MRI system. It's actually putting the subject into the scanner and getting them off, right? Especially people who are sick, it can take some time to actually put them on the scanner. So in hospitals where they're really trying to get throughput, they actually have beds where they'll load the patient in beforehand, and then you save that time where you can just load the bed in and you have multiple beds and you just have them in a queue waiting to go through the scanner. Okay. So for people who are trying to run MRI as a business, undersampling is a way to make more money. But also in certain patient populations, being able to scan faster is the difference between being able to do the scan and not do the scan. And so, for example, in like babies or young kids who it's really hard to get them to hold still for very long, then you'd want to use undersampling, right? So the first way we're going to look at dealing with undetermined system is what's called parallel imaging. And then we might get into compressed sensing probably next time, and then also deep learning next time. So there are sort of two main approaches. One is parallel imaging tries to take our undetermined set of systems and make them well posed. Okay. Whereas compressed sensing and deep learning say, well, let's just use some prior information assumptions to help us make up for that undersampling. Okay, so here's the idea that basically, if I have my full case space here, one way I can go faster is I can just collect the center case space, in which case I can go faster, but now I have a blurrier image. I have lower resolution, okay? But the other way I can do it is I can skip every other line of case space, but now I have aliasing, and so that's the issue, okay? So the idea is if I skip every other line, I have this undersampled acquisition. But then I realized, oh, what if I had multiple coils, right? Then each coil is undersampled, but and each coil sees a different part because of sensitivity. And now I stack up all those measurements. So now I go back to going undersampled. I actually go back to overdetermined. And now I know how to solve things, right? Okay. Because I know I'm going to have a least squares estimate for my solution. Okay. So the acceleration factor is typically how much we undersample. So when I talk about acceleration factor, that's what we mean. And so the idea is we're using information from multiple coils. Okay. So the idea is the signal from each coil can be written with a sensitivity pattern, and we'll generally accelerate along the phase encode direction because remember from our spin warp, that's the slowest direction, right? We're going line by line by line. So we get the most bang for our buck by accelerating this way. And so we can do that. And so let me just skip to sort of the example for the homework. So let's take a look at this example here to show you what we're going after. So here I have my coil profiles from before, right? And so everything up in the first row is the same. And now in the second row, I have my coil one times an object, coil two times an object as before. Now, if I reconstruct each coil by itself, right, using an undersampled recon, I'm going to get aliasing. Okay? But if I stack those two images together and process them correctly, I can get back my reconstructed image without aliasing. So it's sort of a trick. I have two images that taken separately would be aliased, right? And have the image replicated, right? But if I combine them correctly using the least squares estimate, I'm going to get back an image that looks pretty good, right? So that's what we're after with parallel imaging. Now, the trade-off is that it really depends, how will I do, really depends on what those coils look like. And this is what you're going to play around with in the coil profile. Here I've gone back to these two coil profiles that are very similar, okay? And so in this case, the aliased images each look okay, but they're aliased, right? Now in this case, if I take those two aliased images and combine them in a way to get rid of that aliasing, I get a really bad looking image. Okay, so this is now showing you that actually now the coil profiles matter a lot. So to be able to do this, I need coils that sort of are fairly distinct, and you're going to play around with, the effect of that. That's represented by something called a G factor. Okay, G factor is how much that the noise is amplified in your image. So if you look at this scale is from 18 to 19. So this is a G factor of around 18.4, okay, which is a very high G factor. That means noise is going to be amplified by a factor of 18. Whereas if I go back to this one, this G factor is around 1. So this is a really nice coil sensitivity pattern where it's not going to amplify the noise too much. Okay. So let's talk a little bit about how we actually do that. I'm not going to go through the math. I'm just going to give you an example of why this might make sense. So, and then we'll look at sort of why different profiles have different G factors, and then that should give you enough sort of intuition to do the homework. All right. So let's imagine that we have these 4 different coil images. Okay. And you can sort of see what you're showing here is they each sort of have an alias view of the object. All right. And we're trying to figure out how to reconstruct this voxel here. Okay. And what we know is that basically, if I have aliasing, for example, I'm going to have an overlap, right? Okay. So in fact, a voxel here and a voxel here will appear to be on the same place. Okay. So what that means is that, and then also each of those voxels has some coil sensitivity. Okay. So what I can say here is if I look at a single coil image here, okay, then the acquired thing would have, ideally, I would have the intensity of that voxel times its coil sensitivity pattern. And here I would have the intensity of this one times its coil sensitivity pattern. Okay. But what I actually get when they're aliased is I get A plus B is equal to IA times CA plus IB times CB. Okay. right? For the first coil, where I'm going to say that this is the coil one, okay? And so this is for coil one, I'm going to have that. And then for coil two, I can say, well, for coil two, I'm going to have the same thing, but it's for the second coil. And for coil three, it's the same thing, but just using the coil sensitivity for the third coil. And also for the fourth coil, it's the same voxels, but yeah. So it turns out I can write, let's say this, we'll call each of these I1, I2, I3, I4 is equal to CA1, CA2, CA3, CA4 times IA times CB1, CB2, CB3, CB4 times IB. And that's an equation I can solve, right? So that's now a linear equation. So now I can solve, these are my aliased images. These are aliased, right? And these are this is what I want to estimate. Okay. So that's what the recon is going to do. It's going to actually do this in a really clever way. But what we're going to see is it's going to depend on, these are my coil sensitivity patterns, right? It's saying what I measure is a sum of two vectors, right? It's a sum of the first column and the second column, okay? So now we're going to look at why that matters. So if my sensitivity patterns look really similar, those two vectors are going to be very like this, right? The more I make my sensitivity patterns look different, those vectors are going to go away like that. And at some point, they might be even almost orthogonal, right? So we're going to end sort of by looking at why that matters, and then we'll go from there, okay? So we're going to skip all that, and we're going to come to here. So basically, that's what I just said, that let's call this vector one, this is vector two, okay? So imagine if I have these two vectors, right? And they lie in some plane, right? And I have some measurement S, right? And I'm looking for the estimate, the sum of those two vectors that gives me the minimum error. Okay. So let's say I have if these vectors are very close together, right? And there's a lot of noise, right? Then that noise can project down into here. And so some of the time, if the noise is over here, then vector one is going to be my solution. But if the noise shifts me over here, then vector two is going to be the solution. So I'm going to have a very unstable estimate, right? Because either with a lot of noise, either vector one or vector two could be a good solution. So that's why my noise gets amplified. Whereas if I have V1 and V2 sort of distinct from each other, then if the solution is vector one, then even a little bit of noise is not going to be shift me away to vector two, right? It's still going to be something around vector one. Conversely, if the real solution is vector two, if I add some noise, it's not going to really be enough to perturb me to say that vector one is a better solution. Okay, so when both your vectors are similar, then either one sort of can be a good solution. And so you want your vectors to be distinct enough such that it's clear which one is the better solution. Yeah. It is optimal, but you can't actually do it in practice, right? Yeah. Yeah. I mean, there's trade-offs, but yeah. Okay. So let's look at this. So this is getting to now to your related to the homework. So if you look at this, so let's say we had a voxel here and a voxel here, right? So if we looked at the vector, so this would be like, say, 1, 0, right? And then this would be like 0, 1, right? So those are pretty orthogonal, right? So that's why you get such nice performance when the vectors, those two profiles. But if I go here, now I've got like, 0.9, maybe, 0.95, zero point 0.9, and 0.9, 0.95. And so now these two vectors are fairly, look very similar. And so that's why in this case, you get this noise just blows up quite a lot. Okay. So you just want to play around in the homework and just play around with coil profiles and see what happens and sort of see, oh, if I make the vectors look very similar, does the noise blow up? And if I make them very similar, the image should look really bad. And as I make them more distinct, it should look better, right? So that's what you're after. Okay, so that was the G factor, and this is just showing you, for example, how we compute the G factor. And the G factor, all you need to know is it's sort of just bigger is worse. Okay, so once again, this coil profile has a G factor of around 1, and this coil profile has a G factor around 18, right? And so basically, that's the noise amplification factor that you have to worry about. Okay. And then we're going to end with one last thing to sort of continue with this understanding of how the coils affect the recon, which is the other sort of way of doing parallel imaging is what's called grappa. Okay. And it's based on this idea that if I have my object here and I multiply by a coil sensitivity pattern, I basically end up with my object I times some coil sensitivity pattern C, right? So I'm doing a multiplication in the image domain, right? So in the Fourier domain, that means I've got the K-space representation of my object, and now I'm convolving it with the Fourier transform of my coil sensitivity pattern, which is now going to end up to blurring in K-space. Okay, so basically I have my K-space of my image, but now I come along and I sort of blur my K-space. What that means now is the different points in K-space are now related, right? This point in K-space now comes from all the points around it. And this point comes from a similar neighborhood of points. So that means I would expect that different parts, I don't need to collect all of K-space. Maybe I can get away with undersampling of K-space. And that's exactly how grappa works. Essentially, it's saying like, what if I didn't collect this point in K-space? Right? Let's say that was one of the lines I skipped. Well, the neighboring points around it have information about that point because when I blurred to create those points, it had information from that point. So I should be able to use all those neighboring points and estimate back what that point was. And that's exactly how grappa works. Okay. So the idea is I undersample here. I use grappa to estimate the missing samples. And then I basically recreate the Fourier transform I want from every coil. And then I do the sum of squares recon and I get my estimate back, right? And so this is sort of an example of what grappa can do. So for example, this is if I go twice as fast, 3 times as fast, and 4 times as fast. And you can sort of see if I go 2 or 3 times as fast, I mean, the image is still very good. As I start to go faster, I get some artifacts, but it's still sort of, this works well enough in practice that if you get an MRI exam done, you will typically be having some form of parallel imaging. Grappa is a very common form, and typically they're going to be going 2 or 3 times as fast as they could without using grappa. Okay. So yeah, so let's end here. So next time we'll pick up with compressed sensing. So the idea is today we mostly focused on this reconstruction here of solving things in image space, okay? And in fact, what's done in your homework assignment is this sort of solution here, where we're sort of solving that linear equation with the pseudo inverse. But just so you're aware of it, and just so you know that there is another alternative where you could actually just do the reconstruction fully in K-space and then do the sum of squares that we talked about previously and do the coil combination. So they're both used and variations of them are used. And so the bottom line is we have our K-space we purposely undersample k-space so we can go faster, and then we have ways of filling in the missing information. And because we have that, now we've essentially broken the Nyquist criteria, right? We're basically, the Nyquist criteria said you have to sample a certain rate to get not have aliasing, but it turns out if we use information from multiple coils, we can sort of use that multiple coil information to make up for the information we lost that we threw out. All right. And so that's sort of the basis of modern imaging. And then next time we'll go into how we can take that even further by saying we know what images look like. And so therefore we can go even faster. Okay. So I think that's good for today. Are there any last questions before we end? Okay. If not, feel free to ask questions about, oh, I guess the only other thing is we will be posting Project One scores probably either today or tomorrow. So just keep an eye out for that. And if you have questions about the scoring, feel free to ask either myself or Professor McVeigh. Okay. Yeah, you had a question.
Project two.
Sure. Yeah.
So my group was doing project on analysis of fMRI.
Yeah.
Would it be appropriate for us to use like a toolbox in MATLAB, like the con toolbox, or would that be something that should be avoided?
You can certainly use it, but the issue with that is you'd want to somehow like um like if you use it then um like what would be the I guess maybe let me ask you a question. What would be the goal of your what are you trying to do with your project?
Well, we're trying to do some analysis. Like
Yeah.
that's a very broad topic, right? So we're trying to figure out like what can we even do with that?
Sure.
And
Okay.
my first instinct is to use the con toolbox because that's what I already use for fMRI analysis.
Okay. Okay.
So
Yeah, so you could, so directions you can take a project like that, or, you can get into a little bit about, what, why are you analyzing it this way? Like, explain, why the analysis makes sense and, how's it related to the fMRI contrast, for example? Like, what is it about this analysis method that makes sense? And then provide some background on, or, even some simulations of, the analysis. I think the only downside with doing analysis is if you're doing real data, right? It can take quite a lot of time
yes.
to process it, and most of the time is spent on like making the data nice enough. So that may or may not sort of reflect in your project, right? You
Okay.
might spend a lot of time, like 80% of the time, sometimes 80% of the time is spent just getting the data to like look okay, and then
Yeah.
you're left with very little time to do anything
Yeah.
that sort of shows your understanding of you've done a lot of work, but you've spent it, figuring out how to get things to register or, like, you run the analysis and it doesn't look correct. And then, so that's the only warning.
All right.
But if you've already used and you have data that you've already analyzed, then you could just say, well, okay, I've already analyzed the data. So now I'm just trying to understand it a little better and try to use course. Maybe, you can bring, like you can look ahead to sort of the lectures from last year on fMRI and maybe sort of that might help you understand it better, or you can obviously use ChatGPT or anything to understand fMRI better.
All right.
Yeah.
So much.
Does that help?
Yeah, it does.
Okay, sure. Okay, take care.